Let's dive into the fundamentals of object-oriented programming, or OOP, in Python. At the core, we have a class, which acts as a blueprint or model. Inside this blueprint, we define the attributes, which are basically the variables, and the actions, which are functions we call methods. From this structure, we can create an object, which is a concrete instance. Notice how the class provides the overall structure, but it is the object that holds the specific data. Let's look at how this actually lives in the computer's memory. Here is a memory block representing a student instance. Inside it, we have slots for our attributes like name, age, and marks. Below those, we have our methods linked to this specific instance. Out here on the left is the variable s1, which acts as the object reference. It points directly to this memory block, ensuring that when we call a method, the computer knows exactly which object's data to process. Now, how do we write this in code? We begin with the class keyword followed by the class name. In Python, you'll often see object in parentheses, meaning it inherits from Python's base object type. Inside, we define a special method called the constructor. It's written as def init with double underscores. Inside this constructor, we set up our instance variables, for example, setting self.name equal to Vishnu. The self parameter is absolutely crucial. It is a reference to the current object being initialized. When you actually create an instance by typing s1 equals student, three main steps occur in the background. First, memory is allocated. Second, the init method runs to set those initial values. Third, the memory address is returned to s1. You can then access that specific data using dot notation like s1.name. To make our classes more flexible, we use parameterized constructors. Instead of hard coding Vishnu for every student, we can pass specific values when we create them. We define our init method with parameters that can have default values like n equals empty string and m equals 0. Let's look at the examples on the right. If we say s equals student with no arguments, it uses those defaults, so the name is empty and marks are 0. But if we pass arguments like Lakshmi Roy and 880, it passes those into the parameters and assigns them directly to that new object. The most important takeaway to remember is this. The constructor sets up the attributes, but it does not actually create the object itself. The memory is already allocated before the init method even starts running. Next, we'll explore how these instance variables differ from variables shared across the entire class.
Python classes utilize two fundamental types of variables to store data. First, we have instance variables. As you can see by looking at these two distinct objects on the left, instance variables are entirely unique to each object. If you change a variable like x or y in object 1, it does not affect object 2 at all. They are defined inside the initialization method using self. On the other hand, we have class variables. These are defined directly in the class body and are shared by all instances of that class. Notice how both objects s1 and s2 point to the exact same variable n, which equals 10. This sharing behavior is managed through what we call namespaces. Let's look at what happens when we modify a class variable directly within the class namespace. Down here on the left, before modifying, both instances point to the class namespace where n is 10. After modifying, the class variable n becomes 11. Because both instances reference this shared namespace, they both immediately reflect the change and now see 11. However, things change dramatically if we try to modify that shared variable through an instance instead of the class. Looking at the right side of the namespace diagram, initially everything is 10. But when we modify n specifically for instance s1, Python doesn't change the shared variable. Instead, it creates a shadow variable right inside s1's instance namespace. Now, s1 sees its own n as 11, while the class namespace and s2 still safely hold the value 10. Now let's talk about the actions our classes can perform, which are categorized into 3 types of methods, based on what data they access. First are instance methods. These operate directly on instance variables and must take self as their first parameter. They act as accessors to get data or mutators to set data. Second are class methods. These operate on the shared class variables. We mark them with the class method decorator and use class instead of self. For example, if we have a bird class where wings equals 2, a class method would use class.wings to ensure every single bird shares that same trait. Third, we have static methods. These are simple utility methods, marked with the static method decorator. They don't need self or class because they don't modify object state. They are ideal for independent calculations, like counting total objects. Objects don't just exist in isolation, they interact with another. One class can cooperate with another by passing an instance directly into a method. Here, an employee object E is passed into another class's method, allowing us to modify the employee's salary externally without needing complex inheritance. Finally, we can tightly group related structures using inner classes. If a concept strictly belongs to another, like a date of birth belonging to a person, we can define the DOB class entirely inside the person class. We access it logically by chaining them together, like p.dob.display. To wrap up our discussion on object-oriented programming, always remember that classes provide the shared structural blueprint, while namespaces carefully manage how individual objects store and shadow their unique